Hello everyone, my name is Guo Hua. This work was done in collaboration with Zhou Xuan. Here is an outline of this talk. Firstly, I will present the motivation behind this work. Subsequently, I will discuss the framework's design, the basis of our specification-driven development toolkit, and the workflow to use it. Furthermore, I will introduce how to apply the framework, mapping design to implementation. We use TLA plus to model IO automata and verify its correctness. Lastly, I will give a case study about developing the rough consensus protocol. To start, let me talk about the motivation for this work. The development of distributed systems poses significant challenges, particularly in ensuring correctness with the inherent non-determinism associated with such as concurrency and node failure. The design, development, and testing debug process are often laborious and complex. TLA Plus offers a formidable tool for modeling such systems. Yet its primary application lies in the design phase. Ensure the system correctness remains hard if the implementation strays from the initial design. How can we bridge the divide between the design and implementation? What we think is that by ensuring that the implementation is a process refinement of the design. Think the design as a low-resolution animation containing only the keyframes. The implementation, on the other hand, is a high-definition animation that not only preserves the keyframes, but adds more details. This approach ensures a seamless transition from concept to reality, maintaining the integrity of the original design, while adding the necessary details for the implementation. Our basic idea. First, we get the system implementation closely with the specification. Next, we employ a model checker to delve into the valid states of the design. Finally, we generate a test case set from the model to verify the implementation. The step outlined in the test case serve as the keyframes, and we utilize testing to check it. There are several related works in the field of model-driven testing, include Domini, Extreme on MongoDB, and Mockit. Our work goes beyond more than testing and focuses more on the entire engineering lifecycle and keeps the consistency between design and implementation. The architecture of our toolkit includes several tools and libraries that form its foundation. TraceGen, a command line tool that used to generate traces and test cases. The trace serves as the basis of our testing framework. The deterministic player, another component who can execute determinate testing guided by the test cases. Ensure controlled test. Assert is the library responsible for serialization and deserialization. SNIT is a library dedicated to build network channels between testing nodes. By leveraging our assert and SNIT library, we standardize the communication interface between testing node and between testing node and the player. The approach ensures transparency and seamless integration of testing. The workflow. First, we use IO automata to specify the system and identify its input, output, or internal actions. We use TLA plus to specify the automata. Second, verify correctness and create the model's valid state space. Third, create a set of test cases from the model's state space. Fourth, develop a program code based on the specification and map macro in the program, which is mapping the system states to the action of the automata. The later talk will dive into the concept of macro anchor and demonstrate how they aid in finding inconsistency state between the system and the automata. Currently, we only support Rust programs, but introducing an additional adaptive layer could potentially expand our support to other languages. Fifth, deterministic testing should be conducted, and inconsistency between the design and the implementation should be identified. The workflow operates as a continuous and iterative process. We repeatedly undertaking this procedure until the specification is thoroughly verified, and all the test cases derived from the model are successfully passed. This ensures that the system meets the design behavior and perform as expected. We use input-output automata abstraction to formalize the system. The detailed automata concept could be found in the distributed algorithm book. The I/O automata A comprises 4 components. Firstly, an action signature S characterizes the I/O automata through 3 distinct sets of actions: input, output, and internal. Secondly, a state set is defined with a special designated initial state. Thirdly, the state transition relation on the state set. Finally, a task partition represents a group of action sequences forming individual tasks. These components formalize the behavior of structure of the I/O automata. We then define a trace of automata. A trace is a finite sequence of continuous states and the state transition. The trace set would build the final test case input. To use I/O automata, the developer must identify the system events that should be defined as action in each I/O automata, include their respective action types, input, output, or internal. Not all system events need to be modeled. For example, sequential code operating in the same thread with a trail and does not need to be modeled. In contrast, non-deterministic behavior is hard to test and need to be modeled as actions. This non-deterministic action includes node failure, concurrency, and asynchronous messages that can be lost, reordering, or be duplicated. Then, we use automata to generate a trace set. We utilize TLA plus to specify the automata and introduce an action variable to capture the states and action signature of automata. The signature encompasses of various action types along with their associated payloads. Furthermore, we enrich the input classification with setup, check, and message subtypes. The setup subtypes maintains the model's state of the step, and the setup action allows testing to start from a valid system intermediate state. The check subtype holds the expected state for the current state of the model. which is used to find a non-equal state between spec and implementation. The message subtype represents the communication message sent between tasks. Tasks can be partitioned based on threads, processes, or server nodes. We run TLC model checker to verify the correctness. The correct property can include both safety and liveness. We must ensure the model is bounded to generate a finite trace set. To avoid state exploring and control the model size effectively, we employ techniques such as symmetry and view to include some non-essential variables and states. While these techniques can be intricate in generating continuous traces, we assign a unique UUID to each action and record both action's UUID and the UUID of its preceding state. This ensures that only continuous traces are retained for testing purposes. Furthermore, we adopt a staged approach, which we will discuss in our wrapped cases. Another strategy to keep the model size manageable is by setting boundaries for each operator. To achieve this, we introduce auxiliary variables that restrict the number of each large operators, thus preventing the creation of large state space. How do we generate the trace? Initially, we attempt to utilize the dumped dot file. However, this quickly encountered some limitations. This approach is not efficient for large models as it involves significant I/O, serialize, deserialize, and passing costs. To address these issues, we developed a save-value TLC operator. This operator saves action variables to SQLite database for future usage. In each valid next step of action, we employ the save-value operator to store action steps in SQLite file. By adopting this method, we achieve batched I/O operation, reducing amount of serialization and deserialization passing costs. This significantly improves the efficiency of our trace generation process. The algorithm for generating traces proceeds as follows. Initially, the direct graph is read and constructed, with each vertex representing a valid state of automata, and the edge reflecting state transition. Subsequently, the algorithm searches and covers all the vertices. It identifies all strongly connected components with the graph and replaces its SCC with a new vertex, thereby creating a new graph without SCCs. Next, a deep-first search is conducted on this modified graph, and a valid trace set is collected. Finally, the SCC vertex replaces it with a Hamiltonian path to construct the final traces. This process ensures that all relevant states are accounted for, leading to the generation of all possible traces. We implement a system as a refinement of the specification. The system has certain limitations when conducting deterministic testing using the model. You need to eliminate non-deterministic behaviors such as loss or duplicate of messages, or the execution of random generator. All such non-deterministic behavior can be regarded as input actions and simulated as incoming message from network channel. To accomplish deterministic testing, we have insert macro into the source code at the appropriate anchor position. This anchor macro establishes a mapping between the program behaviors and the state of the automata, creating a controllable testing environment. As previously mentioned, we utilize the action variable to maintain automata action signature with TLA+. In the system implementation, action anchor macros establishing a mapping between the system state and the action variables. This macro effect only during deterministic testing. It will remain empty when the system is released for production use. Here is an example of an action anchor macro demonstrating how action variables are mapped to Rust code. Consider Raft vote request message as a case in this point. The action prime keeps the message as the action step of the trace, and the circlet database serves as a repository for storing this value for future reference by test case. During deterministic testing, the player reorder it as order of the trace, and the node and the testing would receive this input message. To conduct deterministic testing, it is necessary for the system and the test to override the network channel and communicate with the deterministic player server. Our S9 and S3 library provide direct support for these functionalities. Testing that is controlled by deterministic player. In a scenario where the player reads a valid trace indicating that the action A1 should occur after A2, but node N1 attempts to initial action A1 first, it must wait until node N2 has executed action A2. The deterministic player ensures this order enforces that A2 precedes A1, regardless of which node attempts to invoke its action first. To facilitate this, the action anchor macro, which is inserted into the system, is responsible for invoking the necessary remote procedure call to maintain the desired action order. If any inconsistency arises between the trace and the tested node action, it signifies a mismatch between the intended design and the actual implementation. The tool detects such inconsistency through the following events. Firstly, if the player fails to receive an expected action at a given step, indicating that the action message, which should be present in the trace step from the tested system, is absent. Secondly, if the player encoded unrecognized actions during a step, this occurs when the player receives an action message from the tested system, but it is not any of the actions specified in the trace steps. Thirdly, if there is an inconsistent state value, this arises when the tested system receives a check input action message, but its current state does not equal to the expected state based on the test. Event E1 and E2 would result in a message timeout. E3 requires the developer utilize an assert statement to report the error. E1 is as loss of a keyframe. An example of E1: when the player fails to receive an action at a given step. Imagine a scenario where the player does not receive the request for action A2. In such a case, The subsequent action A1 cannot proceed, as it depends on the completion of A2. Consequently, the player will time out while waiting for the action from node N2. E2 is like an error keyframe with the object in an error location. The highest point does not appear in the corresponding position in the picture. An example of E2. The player is quoting an unrecognized action during a step. Consider a scenario where the action A1 is not present in the trace. After node N1 sends a request for action A1, expected to receive a notification. However, if N1 fails to receive this notification, it will encounter a timeout. This signifies an inconsistency between the expected action in the trace and the actual action being performed by the system. E3 is like an error keyframe with the wrong object in the picture. We expected it to be a basketball rather than a football. Example of E3. Suppose a situation where after node N1 executes action A1, its state does not align with the corresponding state in the trace. When the testing node checks the received states, it detects a mismatch and reports a non-equal assert error. This requires manual coding within the tested system to ensure accurate state validation and error reporting. The following content is a case study. We employ our tool in development of rough consensus algorithm guided by TLA specification. We implemented the rough consensus protocol, which includes leader election, log replication, log compaction, and node reconfiguration, which is currently under development. We specify rough at two distinct levels: the abstract level and the concurrent level. At the abstract level, we adopt an atomic communication style. On the other hand, the concurrent level utilizing asynchronous communication through send-receive operations. The state defined at the abstract level serves as the basis for generating initial state of the concurrent level. We also adopt a staged approach by dividing rough implementation into two distinct stages, vote and replicate. This stage model is constructed by combining the initial state from the abstract model with either vote or replicate components of a concurrent model. Additionally, we continue to generate valid initial state using the concurrent model and iterative this step with new initial states. We employ a setup consists of 3 nodes and 2 values. Following a series of optimization, the model checker successfully generated over 40 million distinct states, leading to the production of more than 8 million test cases. All these test cases was passed, revealing bugs in both the design and the implementation. We employ our tool and the specifications are openly accessible on GitHub. Our TLA Plus verified rough implementation will also be made available as open source after we complete the reconfiguration protocol and conduct further testing to ensure its robustness. Thank you for listening. I'm happy to answer any questions you may have. Please feel free to email me.